Hello everyone, welcome to Practical Mechanics. I'm Mohsen. Today's video we learn more circle at special cases. When an object is only under pure shear, the element, state of stress is pure shear, or it is a tensile and both sides x and y equal tensile stress. And see, we go step by an example. Show you and draw more circle for all these special cases. Let's start. Consider an element under pure shear. I show you the shear at positive direction because some textbook says that clockwise is tau xy is positive and counterclockwise taken as negative. This tau xy I assume is 50. For example, megapascal. Then we wanted to draw more circle for this particle. How we can apply it to an object? Just by a torsion. By a torque applied to a shaft is under torsion. And then you have a TC over J at the outer sides. If you take an element outside in 2D, you can show stresses like that. Let's draw more circle. First, we draw the how and sigma axis. And this is the origin, zero stress at origin. Then normal stress in both for sigma x and sigma y is zero. They are there. And tau xy is 50 megapascal. Just go by 50. One, two, three, four, five. 1, 2, 3, 4, 5. Positive, clockwise positive, 50 here. And counterclockwise negative for sigma y, 0 sigma y, and minus 50 tau xy. Then, this surface that represents point A in Mohr circle is here. And this surface represents a point B is here. Then draw okay. Okay. Then we reach to sigma 1 and sigma 2 stresses. Yeah. This is sigma 1, which is 50, should be 50, and here is minus 50 is sigma 2. If I wanted to show the state of stress that contains sigma 1 and sigma 2, I must move 90 degrees in Mohr circle, which is 2 theta 1. 2 theta 1 is equal to 19, and an element 45 degrees clockwise. It means that this direction, previous direction, I must move with respect to that direction 45 degrees, half of the Mohr circle. Then that's the surface A after rotation, 45 degrees. And this stress is 50 tensile, sigma 1. And this one is sigma 2 compression. Minus 50. Then we produce this pure torsion, pure shear. Yeah. But we didn't know anything about the tensile stress and compression inside the material. We didn't have any external loading that produced this situation. But as I said, inside the material is not in our control. We apply shear, it fails due to tensile load. If you look at it, there is a 40 degrees angle that it breaks. It means that it resists the pure shear, but because it is a brittle material, cannot resist tensile stress. And fracture happen due to tensile at 45 degrees with respect to the shear that we produce inside the material. Then this angle exactly is 45 degrees angle. That's the site that is fractured. In both fracture happened in the piece of chalk, which is a brittle material. It resists the shear stress, but at 45 degrees, because the shear changes or converted to tensile stress, this cannot resist tensile stress and break at 45 degrees angle. That's the reason that why we have a when it is under pure tensile load, you see we have a flat cross fracture cross sections. Because maximum stress happened normal to the surface, and it cannot resist against tensile stress, brittle material. This is one special case for Mohr circle. Thanks for your watching. See you on the next video.